For the second presentation, please, Mr. Professor Tsuchiui from Japan. Koizumi.
Yeah.
Okay, please. Just a moment, please. This?
Yes.
Okay.
Thank you. My name is Koizumi, the second author of that. Yes. I'll talk about liquid metal embrittlement. Liquid metal embrittlement is a phenomenon that normally ductile metals become brittle if they are stressed in contact with certain liquid metals. This is an example of aluminum specimens. The upper specimen was bent in an inert environment, but the second one, the lower specimen, was bent with a small drop of liquid gallium on the surface. The similar effect is known to occur in various solid metal and liquid metal couples. For example, aluminum, gallium, copper, bismuth, zinc, gallium, etc., etc. There are some characteristics, but we talk about intergranular fracture or transgranular fracture. In most cases, in case of polycrystalline specimens, intergranular cracking is observed. This is a fracture surface of aluminum cracked with a small amount of gallium on the surface. If the liquid metal has an effect in the grain boundaries, single crystal has no effect, has not affected by the liquid metal. But in actually, aluminum single crystal is embrittled by liquid gallium. And single crystal zinc is embrittled by mercury, and so on. But in some polycrystalline cases, for example, this one is the fracture surface is transgranular. So the problem is what determines cracking mode, transgranular or intergranular. In order to understand the mechanism of liquid metal embrittlement, it is necessary to know the cracking mode. For example, recently some computer simulations are made, but the results should be compared with the experiments. The computer calculators say that cracking is intergranular or transgranular. That's the problem. So in this report, liquid metal embrittlement of crystalline zinc will be reported, especially on the transgranular intergranular fracture and its temperature dependence. The experiment is simple tensile test. The specimen shape is like this, and the average grain size is 0.2 millimeters. Strain rate and test temperature range is shown here. Liquid metals used in our experiment is listed here with the melting temperature and eutectic temperature. Then we know that zinc is not affected by liquid bismuth. So in these eutectic alloys, bismuth is used to lower the melting temperature of liquid and tin. The typical strain curves of polycrystalline zinc is shown here. At 353 degrees, the zinc strain curve of zinc is like this, in the case of without embrittler. But if you put a small drop of gallium or bismuth indium eutectic, then the stress strain curve becomes like this. Fracture strain decreases drastically, and the maximum stress decrease, in this case about half, in this case about 1/10. At higher temperature, for example, 423 degrees, zinc stress strain curve of zinc without embritter is like this, while the zinc with a small drop of liquid metals stress strain curves become like this. In all cases, the embrittlement occurs. This shows the temperature dependence of maximum stress and fracture strain. In case of gallium, at the lowest temperature, gallium is liquid. So the whole temperature range, the gallium is liquid. But the maximum stress is lowest and shows a slight increase with temperature here, about 360 degrees. And this, in case of bismuth indium, this is the eutectic temperature of this bismuth indium. And in case of indium, this temperature is the eutectic temperature of indium zinc. Now the fracture stress. In the case of gallium, the fracture surface is apparently intergranular. At high temperatures, the transgranular region increases a little bit. But, however, in case of liquid indium or bismuth indium, bismuth tin, this is indium and bismuth indium, bismuth tin. The fracture surface is completely different. The transgranular fracture stress is observed. For comparison, this is a fracture surface cracked at 77 degrees without any embritter. These stepped cleavage is very similar to this one. In case of fracture surface cracked at 77 degrees, the stepped surface is created because a crack propagates from one grain to the next without grain boundary fracture. So in this case, similarly, the fracture propagates from one grain to the next without breaking the grain boundary. So strength of grain boundary is still strong. But in case of gallium, intergranular fracture occurs, and the strength of the grain boundary is very low. In some cases, for example, aluminum with gallium case, the intergranular fracture occurs, but it is explained that the gallium atoms penetrate into grain boundaries. So in this case, if the penetration occurs or not is examined. A thin plate of zinc was prepared after etching to reveal the grain boundaries. A small drop of liquid metal was placed on the grain boundary and keep it above the temperature, melting temperature of liquid metal, and observed from the opposite side of the droplet. In case of gallium, after 15 minutes, the gallium signal was observed along the grain boundaries. But in case of indium or bismuth tin, there's no trace of indium or tin is observed. So in case of gallium, the penetration occurs along the grain boundary. From the thickness of the plate, penetration speed can be estimated. It was 1 micrometer per second. This is the similar value to the gallium penetration speed in aluminum grain boundaries. But indium and tin penetration speed is negligible small. And we made also a 3-point bending of zinc single crystal in this orientation. In case of gallium and bismuth indium, basal crack on the basal plane is observed. So the cleavage fracture stress is reduced by these liquids. From these results, there are two things happened which should be distinguished. One is penetration of liquid gallium into grain boundaries. That makes grain boundary weak. And the other is the decrease in cleavage strength. This is completely different things. If the grain boundary penetration does not occur, this does not happen. So this leads to the transgranular cracking in the case of zinc indium or zinc tin. If both occurs, in most cases, grain boundary weakening occurs more significantly. So this line reveals and intergranular cracking is observed like zinc gallium case. So this is the final conclusion. Thank you for your attention.
It's okay. We have 3 minutes, so it's time to some questions, please. Remember that we have also discussion after this, all the papers, okay? We need to finish all the time by questions. Any questions? Please. We need questions, please. Okay, thank you very much.